This second video in section 5.3 is going to be a review of the chain rule and how you use it when you have the outside function as one of the area functions that we've been talking about, where the fundamental theorem of calculus applies. So let's write the chain rule. If y is equal to f of g of x, we know that y prime is equal to the derivative of f, the outside function, of g of x times g prime of x. So let's look at some examples that would be just pure review for you. Let's say that y is equal to the square root of 1 minus cosine x. Well, the first thing that you do when you're first learning this, at least, is to make sure that you know what the inside function is, your g of x. Our outside function is x to the 1/2. Our inside function is 1 minus cosine x. So when we differentiate, we know the derivative of f of x, the derivative of x to the 1/2 is, let's write, dy dx is equal to 1/2, not x to the minus 1/2, but g of x, 1 minus cosine x to the minus 1/2 times the derivative of the inside function. The derivative of 1 minus cosine x would be sine x. So that's our derivative. Let's do another example just by way of review. Let's say we have 1 over sine x. You can think of this, if you want, as, well, I would think of it as function composition. You might think of it as sine x to the minus 1 if you want, because you'll be remembering that the derivative with respect to x of x to the minus 1 is minus x to the minus 2, or minus 1 over x squared. So if this is our y, dy dx here will be equal to minus 1 over sine squared x, not x squared, but sine x squared, times the derivative of sine x is cosine x. Now let's do an example where the outside function f of x is one of our area functions. We could make up anything here. How about 1 to x, the integral from 1 to x of the square root of t dt. That fits our fundamental theorem exactly, and we know that its derivative is simply the square root of x. Let's let g of x be equal to sine x. Then, function composition, f of g of x, and this is the kind of problem you'll see in some of your homework, f of g of x would be written as the integral not 1 to x, but 1 to sine x. Sine x becomes the argument of f. F of sine x would be the integral from 1 to sine x. Okay, and we have the square root of t dt. So to differentiate this, let me just call it y right now. So I'll say y prime, or dy dx, would be equal to, okay, the derivative of f at g. We know that, let me get a different color, we know that f prime of x here is the square root of x, and of course g prime of x is cosine x. So we're going to have f prime of g of x, so we will have the square root of sine x times the derivative of sine x is cosine x. Let me make up one more example. The derivative with respect to x of the integral from 0 to natural log x of t squared dt. Okay, our outside function is the integral from 0 to x of t squared dt, and its derivative is just x squared. And maybe we should write that down. let me write. If we're looking at this as an f of g of x, which it is, then f of x is the integral from 0 to x of t squared dt. The argument is the upper limit. So f prime of x, by the fundamental theorem of calculus, is simply x squared. And g of x is natural log x, and its derivative, we know, is 1 over x. So up here we're going to have f prime, here's f prime of g of x. So that will be the natural log of x squared, f prime of g of x times the derivative of g of x. Okay, so here's a tough one. How about if we were given the derivative with respect to x from the integral of x to x squared of t squared plus 1 dt. Well, this doesn't look exactly like the fundamental theorem because we have a lower limit of x, but we could break this into functions that we could use the fundamental theorem to differentiate. So I'm going to rewrite this as the derivative with respect to x of, and I'll just pick any number I want. I'll pick 0. And I'll write this as the integral from x to 0, and I'll skip the t's right now, plus the integral from 0 to x squared. Okay, well here we have a number on the bottom, so this one looks okay. We could just use the chain rule. But this one doesn't fit the fundamental theorem exactly. So here's how I'll do the problem. Rewrite it one more time, and I'll write this as minus the integral from 0 to x, using our properties of integrals, of t squared plus 1 dt, plus the integral from 0 to x squared of t squared plus 1 dt. Now I can integrate each of those. The first one, well, that's just a direct application of the fundamental theorem. By the way, the derivative of the sum is the sum of the derivatives, so I'm just going to differentiate each one. And I will get, well, minus the derivative of this right here. Well, that's a direct application of the fundamental theorem. Minus the quantity x squared plus 1. Minus the derivative of that area function. Now the next one, I'll use the fundamental theorem, but I see here that the upper limit of integration is a function of x, not just x, so I have to use the chain rule. So I will have x squared squared, x to the 4th plus 1, plugging in x squared instead of just x, and then I have to multiply by the derivative 2x. And so this, we might be able to simplify that, but that is the derivative of that function. So you have to use properties of integrals, you have to use the chain rule, the fundamental theorem of calculus.